Alright, so in this video we're going to talk about supernodes and how to solve problems using supernode analysis. It's basically just like a certain form of nodal analysis, and don't get scared away thinking it's like a super hard version or something or super advanced. It's just like a special scenario or a special case, and otherwise it's basically just as easy as nodal analysis. And all you need to do for nodal analysis is just to apply KCL, or Kirchhoffs current law, at all of the unknown voltages or unknown nodes. So imagine you have this problem here where we have two voltage sources and a bunch of resistors, and that we're told that this is our ground, or we define this as our ground to be 0 volts. Then when we cross over this voltage source, we're going to jump up 3 volts. So this node up here is going to have a voltage of 3 volts, and on the right hand side, as we jump across this one, we're going to jump up to 2 volts. And that just means that we're going to have this node, let's call it A, or the voltage at A for its voltage, and then this node over here is just going to have a certain voltage. If this node was called B, then this would be voltage at B, or VB. Now you can solve this problem using nodal analysis. All you need to do is you need to draw on some currents that you think. So let's just assume some directions for currents flowing across these resistors, and then we would just write KCL for node A and KCL for node B. And we could write expressions for these currents by simply just rearranging Ohm's law, which is V equals IR, and we can just rearrange this to be I is equal to V over R. And notice that we have two unknowns, VA and VB, and two equations, so this problem is solvable, just using KCL and Ohm's law. Now imagine that there was one more voltage source in this problem. Then we can't just simply write Ohm's law across the battery, V equals IR, and know what it is, because we don't have enough information here. So this problem cannot be solved with basic nodal analysis, but we can use what's called a supernode. So what you do is we basically want to join these two nodes together, because we still have two unknowns. There's just VA and VB, so all we have to do is come up with two equations. But like we said, we can't really know exactly what the current is between VA and VB right now. So what we do is we just join them into one single supernode. Basically just put like a dashed line or draw a box around it. And what we can do is we can apply KCL at this whole supernode, basically including A and B. So we just want to sum up all of the currents flowing in and set them equal to all of the currents flowing out. So let's get rid of these expressions, because this was for the previous version. So we can write this as KCL of our supernode. And we're going to basically just have I1 flowing in and also I5 flowing in, and then the ones that flow out are going to be equal to I2 and I4. So this is one of the equations that we're going to use, and we're also going to substitute in Ohm's law here. And the other equation that we're going to use is just sometimes called the supernode equation, and it relates VA and VB as well. But we can see here that VA is just 1 volt higher than VB. So the supernode equation is just VA is equal to VB plus 1. And now we have two equations and two unknowns, and we're going to be able to solve this problem. So that's all supernode is. It's not very complicated. It's no more difficult than a basic nodal analysis problem, but you just have to identify a supernode, and basically that's just going to be one node connected to another node with a voltage source. Just draw a border around them and treat them as the supernode, and then proceed with these steps. So let's actually fill out what we have for I1, and basically again we're going to substitute across the resistor. It's going to be the voltage drop across the resistor divided by the resistance. So for I1, the voltage drop is going to be 3 volts minus VA. That's because we're going from the higher side to the lower side, because we've assumed this is the way that the current is flowing. So the difference, the voltage difference across it, is basically, the higher side minus the low side. And then we divide that by the resistance, which is just 2 ohms. And then for I5, we're going to do the same. So we have the voltage is 2 volts minus VB. So we can write that in, 2 volts minus VB. And this is all over the resistance, which is 1 ohm. For I2, we're just going to have VA minus 0. So that's just going to be equal to VA over the resistance, which is 3 ohms. And then for I4, it's exactly the same. We have VB minus 0, which is VB, over the resistance, which is 2 ohms. What you should do now is just multiply each term by the lowest common denominator, which is going to be 6. So we can just write a 6 in front of each term here. Hopefully this doesn't get too messy. And then we can simplify a little bit. So 6 divided by 2, this is going to end up being a 3. The 6 is going to stay. This means we're going to end up multiplying this term by 2, and this one ultimately will multiply by 3. So let's just clean this up, and I'm actually going to drop the units of volts and ohms because we're using V as the name of a variable and a unit, and that just gets a little bit messy. But basically we can just keep simplifying this, and we're going to end up with 21 is equal to 5VA plus 9VB. But we have an expression for VA here, which is this guy. So what we can do is we can basically combine these, and we'll get 21 is equal to 5 times VA, which is VB plus 1 plus 9 VB. And then we can just continue to simplify this, and we're going to find that VB is equal to 1.14 volts. And then we can just plug this right back in because VA is just equal to VB plus 1. So VA is just going to be equal to 2.14 volts. So if you want, you can drop a box around that because that might be the answer that you were asked for initially if you're just basically asked to tell what are the unknown voltages at VA and VB, or sorry, node A and node B. And if you were asked to actually solve for all of the currents through every resistor and all of the voltage drops, you could really easily do that by just applying Ohm's law over and over and over again. But I won't bore you with those details in this video. So anyways, thanks for watching, and I'll see you in the next video where we'll go over another example of supernodes.